All right, so we're gonna go ahead and continue on what we were talking about last week, which is acid-base equilibria, which is very similar to chemical equilibria, except now we're talking about acid-base equilibria. And there's going to be a point in this presentation or this lecture where I'm going to have to say you're welcome again, and it's not going to be because of a chart, but you'll see what I'm talking about when we get there. Okay. So, like we were talking about last week, water is amphoteric, right? And so what happens is that water can do this thing called autoionization, right? And autoionization means that water can, if you put two water molecules together, right, one H2O and another H2O, put them together, one of the H2Os can accept a proton, right, and the other one can give up its proton. And so you end up with the hydroxide ion, which is basic, right? And then you also end up with the hydronium ion, which is acidic, okay? So when you're looking at this particular reaction, this equilibrium reaction, right? Since water can act like a base and an acid, right? You can still go through and assign conjugate base and conjugate acid, right? So if this is the acid right here, oopsies, dang it. I always forget to make the pen work. There we go. If this is the acid right here, right, that's the guy that's going to be losing its proton, right? So its pair, its conjugate base pair, is this guy over here, right? And then the one that's receiving the proton, which is this base right here, right, that water molecule too. And so this over here is its conjugate acid. Okay, so don't forget that you need to be able to identify the difference between a conjugate acid and conjugate base from the reactants, right? And you can do that with water, even though water has, even though water is both acid and base, right? Both acid and base. Okay, so we have this thing here that you should recognize. It's called the Kc, or the equilibrium expression, right? And so for the process of water doing its autoionization, it's going to be the concentration of hydronium times the concentration of hydroxide, right? The kind of concentration of hydronium times the concentration of hydroxide. And that was really loud in my ear just now. Just got an email. Anyway, so the special equilibrium constant is referred to as the Kw of water. And so whenever you have this right here, the autoionization of water, hydronium times hydroxide, it doesn't, you can call it the Kc, which is the equilibrium constant generally, but since it's water and water is so special, we call it the ion product constant for water, which is Kw. So the Kw, right, the Kw at 25 degrees Celsius is 1.0 times 10 to the negative 14. And you're going to start seeing how useful that is in just a second, okay? So before we jump into the numbers so deeply, let's make sure that we understand what's happening here, right? In aqueous solutions, they can be acidic, basic, or neutral, right? And in a neutral solution, you're going to have the same number of protons or hydronium ions, right? Just be aware that I can go back and forth, right? If I say protons right here, this can also be what else? It can also be the hydronium ion as well, right? I use those two synonymously, right? I can interchange those two. They mean the same thing to me, okay? Anyway, so if a solution is neutral, right, the hydronium ion is equal to the hydroxide concentration, okay? And then if a solution is acidic, then the hydronium ion concentration is actually higher than hydroxide ion concentration, which makes sense, right? Because the more protons or the more hydronium ions you have, the more acidic you are, right? And then on the other side of the pH spectrum, which we'll talk about in a second, right? If a solution is basic, we actually have more hydroxide ions than hydronium ions or protons, okay? So big thing here, just remember I'll use hydronium ion and proton interchangeably, okay, when I say that, so don't get confused. Okay, so here we have hydrochloric acid, right? Hydrochloric acid, which is a very strong acid, meaning it pretty much 100% ionizes, right? And so the concentration of hydronium or protons is going to be way greater than than the hydroxide. In a neutral solution of water, it's going to be pretty much equal, right? But that's even more complicated than you think. You don't have to worry about that now. But for the purposes of this, right, it's going to be equal. And then for a basic solution, hydroxide will be bigger than, will be more concentrated than uh, hydronium or proton. But the thing I want you to really notice about this whole thing is that no matter how acidic or how basic or how neutral it is, right, you always end up with 1 times 10 to the negative 14, right? You always end up with 1 times 10 to the negative 14, okay, when you're talking about the kW, okay? Doesn't matter what you have, you're always going to end up with 1 times 10 to the negative 14. So your first question is this: which of the following is true about a neutral solution? Is the hydronium or the proton concentration equal to the hydroxide? Is the is the hydronium or proton concentration greater than the hydroxide, or is it less than the hydroxide, or is it none of the above? Are you guys glad that we're like in the last leg of the semester? Like school, almost time for Christmas break. I didn't even know that we don't even come back to school till like January 24th. I mean, I'm gonna have like up 2 months off after we get it done. Yeah. I still get paid too, so it's great. Yeah, I checked because I teach forensic science in the spring, and that class doesn't start to January 24th. So it's crazy though. I didn't know we started school so late. Crazy, crazy, crazy. Does anybody know what the last day of school was? So the week of the 14th would be the week of finals? Yeah. So I'll have the 2 weeks, so it won't be a full 2 months off. Hell if I know. What's up? You can drop a lab, but you're still responsible for the report that comes from it. From your partner or somebody in the class? Why, are you missing a lab? On Wednesday? Really? This week or next week? Next week. What? Well, worry about that next week then. It is important, but
I'd rather drop a lab that, I get a bad grade on.
I mean, there's really no way for you to, because we only have one section of the lab, so it has to be done that day. So, yeah. When is the game? Is it? Are you going to be like gone all day, or is it?
November 3rd. I was like October 3rd.
Are you going to be gone all day?
Like warm-ups and shoot around and stuff is around like 12-ish.
12-ish. Oh.
And then it goes on the rest of the day.
I mean, honestly, your lab grades are all pretty much good. I mean, really, the thing that you need to worry about mostly is the reports, right? Because your lab grade itself is not the report grade. It's you turning in the data, you doing your PowerPoint, your pre-lab, you doing your, that kind of stuff. So, I mean, you can drop that easily, and the other ones are still. Have you been turning in all your labs?
Yeah.
So what's the problem? I mean, the reason why I asked.
I just always got one grade. Always got one grade. I don't want it to be that one.
I mean, I honestly would just drop that lab. I wouldn't worry about doing a makeup because you can get the data from somebody else, and I mean, unless you don't turn in any work at all for the actual pre-lab or the data part, right? I mean, you should have near perfect lab scores. I don't know for a fact that you do, but I don't know how you can, so sorry, it's not letting me log into the computer for some reason. And then Mary here is distracting me with her craziness. When, that's not new though. Should be I should already be used to that. I forgot to show you the results. Okay, so the vast majority of you got that correct. The answer is quite literally A, because A is equal to equal to equal. A is equal, right? Hydroxide and hydronium ions should be the same in a neutral solution. So, what does it mean then? What does all this mean? What is pH, right? Well, pH is a method of reporting the hydrogen ion concentration or the hydronium ion concentration. Just remember again, I might put in there H3O plus instead of just hydrogen plus, right? So make sure you know the difference, or not the difference, but know that they're the same. And so when you do pH, right, pH literally means the negative log of the hydronium ion concentration, okay? Everybody should already know, though, that the neutral pH is 7, an acidic pH is below 7, and then the basic pH is above 7, right? And so on this little chart here, which I should have made a lot larger, I apologize for that, but the highest pH you can get, right, is 14, and the lowest pH you can get is 0. Why is that, right? Why is the pH scale 0 to 14? Well, remember, right, no matter what you do, no matter what acid or base you have, right, and whatever concentrations you have it, it's always going to end up the hydronium ion concentration times the concentration of the hydroxide always equals 1 to the negative 14. And why does it always do that? It's because Kw is 1 times 10 to the negative 14, right? And that's the reason why the pH scale is 0 to 14. Does that make sense? Right? So mathematically, it bornes out that the pH scale can go no higher than 14. Interestingly enough, though, you can get some acids that are super, super strong, and it can go way past 0, like go into the negatives, right? But you can't get bigger than 14. So catching back up again, right? Only the digits after the decimal point are significant figures and logarithms. And so if I were to give you a hydronium ion concentration, all you need to do is do the negative log of that hydronium ion concentration. Was she in there? And so if I give you the hydronium ion concentration, all you have to do is take the negative log of the hydronium ion concentration, and you'll get the pH, right? And it'll fit on the pH scale. And so notice here, right, is you have a pH, which is the negative log of the hydronium ion concentration. You can also have a pOH, right, which is the negative log of the hydroxide ion concentration, right? So you have a pH and you have a pOH. That all you add those two together, it should equal 14, right? Because you can go no higher than 14 on the pH scale, right? So this is just some examples of stuff. Human blood is neutral. Seawater is slightly acidic. I mean, sorry, slightly basic. Other household ammonia, household bleach, all that stuff is basic too. And then on the other side of the spectrum, right, you have stomach acid, which is super acidic because stomach acid actually is hydrochloric acid, so that's a pretty strong acid. Does anybody know why hydrochloric acid doesn't burn a hole straight through your stomach? Yeah, so there's a mucus lining on the inside of your stomach that keeps you from getting burned. But so when you throw up after being drunk after a night, right? Your throat like burns, and the reason why your throat burns after you throw up is because that mucus lining is not in your throat, right? But it is in your stomach. What was I thinking? Oh yeah, so there's other pH scales too, like I was talking about before. If you have pH, that's the negative log of the hydrogen ions or hydronium, but you can also have pOH, right? Like I was saying before. And so if you have pOH, right, then that's a negative log of the hydroxide ion concentration. So you can use either one to figure out what the concentration is of hydroxide, or or pH to figure out the concentration of hydronium ions, right? And then you also have the pKw, right? And in the pKw, right, that's just doing the negative log of the 10 negative log of the 1 times 10 to the negative 14, and that actually gives you 14, I think. So, that's the kind of thing you can do with that. So here's some examples, right? Oh, I was right, man. I'm so good at this. Um, anyway, so remember, right? Just a reminder here, right? You can do the concentration of hydronium times the concentration of hydroxide, and that should give you Kw. And Kw is 1 times 10 to the negative 14. And again, the 14 is indicative of the reason why we have 14 as being the highest number on the pH scale, right? So what you can do then is you can take the negative log of the hydronium ion concentration plus the negative log of the hydroxide ion concentration, and that should give you the negative log of the Kw, which is 14, right? And so that's how you can get down here to this point here where it's pH plus POH equals the pKw, which is equal to 14, right? So you'll get problems from me. You'll get questions from me in the assignments and in the quizzes and in the exam that tell you I'll give you this concentration of something, and you'll have to use you'll have to use these relationships right here to figure out, what the pH is, what the POH is, what the concentration of hydronium is, or the concentration of hydroxide is. Okay. So your next question is this: what does the P in pH tell us? What does the P in pH tell us? Acid-base chemistry is actually one of my favorite chemistries. I feel like I say that about everything. Because I just told you my favorite chemistry was kinetics, didn't I? Oh, that's funny. That's so funny. My mood is so changeable. All right. Let's see here. P. I've got 4 responses so far. I got 4 responses so far. Waiting for a couple more. That should be everybody. All right, so the vast majority of you got that question correct, right? The answer is, in fact, B, right? The answer is, in fact, B. And the reason why it is B is because, like I said in the previous slide here, right? Negative log right here, right? Not negative log, P here, right? pH here is the same thing as the negative log of something, right? And so in this question, what does the P and pH tell us? It's the negative log of a quantity. So don't confuse that with ln, which is the natural log, right? There's the natural log and then there's the negative log. Those are 2 different things. Don't get that confused, right? And then you have e raised to the quantity. If you remember what e is just a number, a constant number like 2.7153555389 or something like that. But the only part you need to remember is the 2.71 part. But that has nothing to do with this, right? That has nothing to do with this. And then 10 raised to a quantity is something else we'll do in a second. Okay, so how do we actually measure pH, right? How do we actually measure pH? One way to measure is using a pH meter. Okay, pH meters are used for the accurate measurement of pH. Electrodes indicating small charges in voltage can detect pH. And so this is a very simple, very old school pH meter, right? No, not old school, but like it looks old to me. And you can stick it in there, and you can see that we got white vinegar here, and white vinegar here has a pH of 2.45, right? A pH of 2.45. And so when you have that pH, quite literally, if you have a meter, right, and you stick it in if you have that meter and you have just some unknown solution, you don't even know what the solution is, and you have that pH meter and you stick in the pH meter into the solution, it gives you pH. What can you find out from that? You can find out the hydroxide ion concentration. You can get the hydronium ion concentration. You can get the POH, right? You can get all kinds of stuff. Okay. And the one thing you can do is that if you stick it in there and it reads 7, you know it's safe to touch because it's neutral, right? But if it's going to read 2.45, maybe you shouldn't touch it because it's a little bit acidic. Well, vinegar is not that dangerous, but take it down to 1 or less than 1, then maybe you shouldn't touch it. Have you ever used bleach and you got some of it on your hands and you can feel it getting really slippery in your thumb and your finger when you do this? It gets super slippery. That's because that bleach is actually breaking down the the cell membranes of your skin cells, right? You leave it there long enough, you won't have anything on your epidermis left, right? And so that's what bleach does. Okay, it oxidizes your bleach is actually a molecule called sodium hypochlorite, and sodium hypochlorite is a super strong oxidizer. That's why it kills germs so easily, right? And so not only can it break open the cells of germs, it can also break open the cells of your skin cells, right? And it's literally killing your skin cells when you feel that soapiness, right? You feel that soapiness, that slipperiness, right? And that's why you got to be super careful about that, right? Back to the topic at hand, right? You can use a pH meter to figure out what the you can use a pH meter to figure out what the pH is of a solution, and I might give you a problem on an exam or a assignment or something that says, "Hey, I have an unknown solution of this pH, right? Figure out all this stuff for me." Right? That's the kind of question I might ask you. Okay? So, how do we measure pH? Well, another method is with indicators, right? So, I don't know if you guys ever did this in elementary school or in high school. People can use what is it called? Cabbage water, red cabbage water, right? You can boil cabbage water, and uh, and it will be this like really dark purple color. But you put it into certain acidities or certain basicities, and it will change the color, right? Huh? Because red cabbage is purple.
Oh, I was confused because you said red cabbage.
Well, I think they call it red cabbage, but it's actually purple colored.
I don't eat cabbage. I love cabbage.
That's a weird question to ask. I guess it makes sense. It makes sense. So another one you'll use is called phenolphthalein, phenolphthalein, which is this right here, right? And notice the pH at 10 is super pink, but when you get to like acidic, it's colorless. And the reason why I bring this up is because next week in lab, you'll be doing a titration experiment where you use phenolphthalein, okay? And that's the colors you'll have. Okay, depending on how basic something is, or how basic something is, how basic something is, or how acidic something is, right? So this is just a list of different indicators you can use, right? For methyl violet, right? If you're at the basic level, it's yellow to violet, right? Whereas over here you have alizarin yellow, and it's like red. It's red to yellow. So you can use all kinds of different. I don't want to go through all those different indicators, but the one that you will use for sure is phenolphthalein, and phenolphthalein will be pink to clear, right? Pink to clear. So let's discuss strong acids, right? You will recall that the 7 strong acids are, oh my God, see, this is a you're welcome moment. These are the 7 strong acids right here. So if I ever ask you a question like, which of the following is a strong acid, right, you should know which one it is, or which of the following is not a strong acid, right? So we have strong acids here: hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, uh, sulfuric acid, chloric acid, and perchloric acid. Those are all very strong acids. Okay, these are by definition strong electrolytes and exist totally as ions in aqueous solution. So what happens here is when you have this strong acid HA, you add it to water, right? And what do you get? You get completely hydronium ion concentration and hydronium ions and the conjugate base, right? So for a strong monoprotic acid, the hydrogen ion concentration will equal the same concentration as the acid itself, right? So you have 12 molar hydrochloric acid, right? That will also be the concentration of the hydronium ion concentration. Does that make sense? It will always be the same because they disassociate completely. Strong acids do, right? If I have nitric acid and the nitric acid is 2 molar, right? Nitric acid, then the hydronium ion concentration will also be 2 molar. Okay. Contrast this though with weak acids in a second, right? Because we got to talk about strong bases first, right? Strong bases are soluble hydroxides, right? Which are alkali metal. Strong bases are soluble hydroxides, which are alkali metals and heavy alkaline earth metal hydroxides. So things like calcium, strontium, and barium, but their solubilities are low. But again, these substances dissociate completely. For example, when we have here some metal, say sodium with hydroxide, you get the metal ion there, and you also get the hydroxide ion, right? So when you have a strong base, it's the same thing as it is with a strong acid. The concentration of strong base, so you say you have 2 molar sodium hydroxide, the hydroxide concentration will also be 2 molar, right? for strong bases. Okay. Let's see here. Strong bases are soluble hydroxides. Yes, yes. Let me make sure I got this all written down or told you. Yeah, yeah. So this is your next question. Which of the following is not true about strong bases? Uh, Strong bases are soluble hydroxides. They dissociate completely in aqueous solution. They consist of a transition metal, or all the above is true about strong bases. And I'll tell you now, we're not going to do a lot with strong bases in like the actual gist of this lecture, but you still need to know what they are. We're really going to focus on weak acids and weak bases because those are the ones that actually go to an equilibrium concentration that is different from the acids concentration. Huh? Did you say you'd be the perfect? Did you say you'd be the perfect murderer? You know this is being recorded, right? You know this is being recorded.
So if you do a murder, you need to do it in like Canada or something. They didn't list this conversation. No, because our teacher, he was like those weird goth teachers that always talking about like weird stuff. So we were talking about death or something, and it was Halloween time.
Okay, check this out. I'm very proud of most of you here because the answer to this question was actually C, and half of you got C. Right? It was a little tricky here. Okay, because I told you in the previous slide that strong bases are usually of the alkali metals or heavier alkali earth metals, right? And so C is the one that's not true because it doesn't really consist of the transition metals, right? So good job on you if you picked C there. You were paying attention, or at least you remembered what I said. So good job on that there. I'm going to move on from the conversation that one of my students is going to be a good murderer, and we'll just keep on going on that. We'll just forget that happened. Okay. All right. So this is what we'll focus on here in class mostly, right? And it's the dissociation of a weak acid, right? Where we have an acid, say acetic acid, plus water, right? Will get you the hydronium ion, right? And its conjugate base. And notice that it's a reversible reaction because all equilibrium reactions have arrows going forwards and backwards, right? Notice that compared to that, notice compared to this, right? Where the arrow is only going one direction. When the arrow goes only one direction, it goes completely to dissociation, right? It doesn't go back to being what it was before, right? Same thing here, right? Strong acid to water has only one arrow, right? But when you do a weak acid to water, you actually get a reversible reaction. And the reason why is because not all of the acid will actually dissociate in the water. And so you get some original acid left over, and you get some of the acid disassociated, right? So that equilibrium is known as the acid dissociation constant, okay? Also known as Ka, right? And so, and it's the same as every other reaction we've done in this class. When it comes to equilibrium expressions, we always have the products over what? Reactants, exactly, right? We always have the products over the reactants. So here, the products are the H3O and the A minus, right? And then the reactant here is the original acid, okay? So if the larger value, so the larger value of Ka, the stronger the acid, right? So the larger the value of Ka, the stronger the acid. So you'll see that most of these will have lower Kas because of weak acids not being able to dissociate as well. So here's a list of weak acids, right? Here's chlorous acid, hydrofluoric acid, nitrous acid, benzoic acid. The one we'll talk about the most here is acetic acid. Phenol is also weak acid too. Hydrocyanic acid, hypochlorous acid. Those are all weak. And notice, right, that their Kas are all super close to zero, right? -2, -4, -4, -5, -5, -8, -10, -10, right? So they have very small Kas. So if you see an acid, right, and it has a Ka that's super close to zero, right? Like with these exponents, these negative exponents on the scientific notation right here, right? Know that it is a weak acid. I might ask you a question. This unknown acid has a Ka of 1.8 times 10 to the negative 8, right? Is it a weak acid or a strong acid? It's a weak acid, okay? Make sure you know that difference, okay? So when you're looking at then the comparison between a strong acid and a weak acid, right? What is present in solution for a strong acid versus a weak acid? Well, strong acids, like I said just a second ago, will completely dissociate into ions, whereas weak acids only partially dissociate. So here we have a strong acid, right? Here we have a strong acid, and here you can see that there's half the amount of the particles here are H3O, and the other half is conjugate base, right? By the way, if you're not familiar or if you don't remember, right, um, the in the general sense, whenever I say A minus like that, right, that's a conjugate base, right? That's a conjugate base. And then H3O is the conjugate acid, right? And conjugate bases always have a negative sign, by the way. And you see here that in a strong acid, there's 1, 2, 3, 4, 5, 6, right, of the conjugate base. And then 1, 2, 3, 4, 5, 6 of the conjugate acid, which is the hydronium. So every single ion of this acid broke apart into its conjugate base and made H3O. But when you come over here to weak acid, right, it only partially dissociates, right? Here's one H3O molecule, right? Only one, but the rest of them have stayed, right, together. See? The rest of them have stayed together, right? Not as many H3O, almost no H3O molecules at all. Most of them stayed the original acid, for example, acetic acid. So the point of this is that acetic acid being the weak acid, right, will stay together most of the time, right, leaving you with mostly water and acetic acid. Whereas hydrochloric acid will break into, because it's a strong acid, break into hydrogen ions and chloride ions completely, right? And so when we do equilibrium equations, or we work on equilibrium, when we work on equilibrium expressions, it will almost always be with a weak acid. Okay, almost always be with a weak acid. Okay. So next question: in the equation for the dissociation of a weak acid, what is A minus? So far, everybody's got it right. Oh dang, someone got it wrong. I don't have to see who this person was. I'm gonna have to see who this person was. It was probably the same person that got it wrong last time. Got five more. Five more. Five more. I'm still waiting for 5 responses. I literally just said this on the previous slide. Still waiting for 4 people.
I have a question.
Sure.
Did you explain why a strong acid completely dissociates
Not specifically, no.
versus okay.
Honestly, because you don't really need to know that, right? Because I'm not going to ask you about it. But if you want to know, I'll tell you, right? So if you think about it, right, water, right, is polar, right? It's got the positive side with the water, the H's, and the negative side with the oxygen. And then so when you have something like hydrochloric acid in there, one side's super negative and the other side's super positive. So the water can go around and solubilize it, right, and make it completely dissolve, right, just like it does with salt, right? But then you have something like acetic acid, right, that has a whole bunch of carbons, And so it makes it a lot less polar, right? And since it's a lot less polar, it'd rather stay together than break apart with water. Does that make sense? Yeah, it's absolutely about what we call the intermolecular forces, right? Like polarity, dipole moments, ion dipole moments. So it's a good question to ask, absolutely, and you'll dive deep in that later, but not right now. Okay, so the answer is for this one, absolutely, the answer is in fact D, right? Because it is a conjugate base. A minus is a conjugate base, right? So good on y'all for getting that one right. Good on y'all for getting that one right. So given all this information, right? Let's see how we do this. How do we calculate a Ka from a pH? Given that I have a pH of, the pH of a zero point 0.1 molar solution of formic acid, right? So notice how there's a carbon there, some oxygens, and a carboxylate there, right? So this is going to be a weak acid because there's carbon in there. But anyway, at 25 degrees, is first thing I want to tell you is because I feel like a lot of times we're having issues pulling out the correct information to do a problem, right? Um, if there's nothing else but the 25 degrees here, right? You don't need the 25 degrees for anything, okay? Don't dwell on that, okay? Do not dwell on that, okay? Because in my expression here, is there a big T in there anywhere? No, so you don't need the 25 degrees. We're giving you the extra information to confuse you, but don't be confused by that stupid trick, okay? So I have formic acid, right? I need to find a Ka, and its pH is going to be at 2.38, right? And so how do I do that? How do I figure that out? Well, the first thing I can do here is figure out the fact that we have here the the formula, right, for the formula for formic acid, okay? And the thing that you've got to figure out is, and it already tells you there anyway, but I would, if I were you, write it out so that you know what it looks like. Be like HCOOH, right, plus water gives you H3O plus, right, plus HCOO minus. Okay, I'll write it out like that, just so you know what the actual equation is. The good thing about writing it out too is you can figure out whether you need to have any kind of coefficients and stuff like that too, making sure everything is balanced. But usually though, with these monoprotic acids, monoprotic means one proton acids, right? It's always 1-to-1 ratio. Okay, so this part right here will be at the top of the expression, the H3O and the HCOO minus, right? The formate ion. And then on the bottom will be the acid and the water, but the water, you don't have to worry about the water, right? It's just going to be the acid. Sorry about that. Okay? And so now that you have that, you can fill out the Ka expression, H3O plus times the concentration of HCOO minus divided by the uh, uh, unionized acid, which is the formic acid, right? So to calculate the equilibrium, we need, to calculate the Ka, we need the equilibrium concentrations for all three things. Okay? We need the concentration of all three things. So here we go. We can find the HCl concentration because it's the same as the HCO minus concentration from the pH. Okay, so when you have the H3O concentration, that's going to equal the HCO minus concentration, right? And you were given in the previous problem here, you were given the previous, not in the previous problem, but in the problem itself, that the pH was that, right? 2.38, right? And so you know that pH equals the negative log of the hydronium ion concentration, right? So we take it over here, right? To undo a negative log, what do? You do 10 to that number, right? You do 10 to that number, which, by the way, if you have your calculators here, I'll show you how to do that, right? Because you're going to need it later. Does anybody have their TI-30 with them?
No, I got this.
No, not that one.
I got this right
Yeah,
here.
that works too.
No, it goes to the side. It does all the other.
No, you're only supposed to be using a TI-30 on the test, though. I want to show it on TI-30 calculator first because most people have a TI-30 calculator. Anybody have a TI-30? Thank you very much. There we go. Okay, so I should have brought mine. Oh well. I need to stop asking students to provide me with the tools I need to teach. Here we go. So on this calculator right here, right, there's a button right here just above. Ooh, that was bright. There's a button right here just above the log button that says 10 to the x, right? That's the button you should be using. Okay? That's the button you should be using, 10 to the x. And so it's 10 to the x, and what is the x? It's that negative pH right there, right? So to undo a log on this side, to undo a negative log on this side, right, of the equation, you've got to do 10 to the negative pH. Make sense? And then vice versa, right? To undo a 10 to the negative pH, what do? You take the negative log, right? One undoes the other. Thank you very much. So don't forget the 10 to the x button on your calculator. And when you do that, you do 10 to the negative pH, and you get 4.2 times 10 to the negative 3. And that's the concentration of the both the H3O and the HCOO minus. Okay? So then we take it to our ice table. Oh, you thought we were done with ice tables, didn't you? Because you thought, oh, in solution equilibrium we did ice tables, but we're done with them now, right? No, we're not done. So now we can set up our ice table, right, where we know that the initial concentration, right, of the formic acid is 0.1 molar, and then we also know that the ion concentrations in the beginning is 0 molar, right? And then we find the equilibrium concentrations by plugging in that number that we found, right? That number that we found just in the previous slide, so that we can figure out what the equilibrium concentration is, okay? So notice here, I mean, there's the equation that I wrote out for you just a second ago, right? Formic acid becomes hydronium ion or protons plus the formate ion, right? So in the table, we start out with the initial being 0.1 because that was given in the problem, right? And of course, this is initial, so there should be 0 H3O plus and 0 formate ion, right? But then we found out in the previous slide when we did the 10 to the negative pH right here to figure out what the concentrations were, right? That the concentration change, right, is 4.2 times 10 to the negative 3 molar, right? So that what that means then is that as we reach equilibrium, right, this initial concentration of formic acid will be subtracted by the uh, the 4.2 times 10 to the negative 3, right? Because that's how much of the initial concentration of formic acid we're losing. So if we're losing that much on that side, the reactants, where is it going to go? Exactly, it's going to go on the product side. So that's why on the product side, you have plus 4.2 times 10 to the negative 3 and plus 4.2 times 10 to the negative 3, right? So all you have to do now is figure out this math down here for the equilibrium concentrations, right? We don't have to do anything with that at all because it's just plus that, and you'll get these, right? Because they were 0 before. But over here, you do have to do the subtraction of 0.1 minus 4.2 times 10 to the negative 3 and get you that number right there. And that will give you the equilibrium concentrations, okay? Once you get those equilibrium concentrations, all you have to do is put it all together in the Ka expression, right? 4.2 times 10 to the negative 3 times 4.2 times 10 to the negative 3. This was the hydronium ion concentration. This was the formate ion, right? And this is the formate, right? And then this was down here, the original concentration of the acid, which was the formic acid concentration, right? So you plug them all in to the Ka expression, and you get 1.8 times 10 to the negative 4. And that's the Ka of formic acid. Good stuff. Good stuff. So the next thing you can do is you can calculate the percent ionization, right? Where you take the concentration of H2O at equilibrium divided by the initial concentration, which was the 0.1, and multiply it by 100. So in this example here, our concentration of H3O, remember we calculated it to be using the 10 to the negative pH equation, calculated to be 4.2 times 10 to the negative 3, right? And then the problem gave us that it was a 0.1 molar solution of formic acid. So you just plug it in there, right? Um, Products overreacted again, right? And times 100, and then you get a percent ionization of 4%, right? So it's super easy to figure out the Ka of the equation of the acid base problem, and figure out the percent ionization just by knowing what? The pH, right? And the original concentration. So, real quick here, next question. In the example with the dissociation of formic acid, the H3O concentration is equal to what? All right, let's see how people are answering this question. Oh, so far everybody's got it right. But there's only 4 people, so 5 people now. Woohoo! Still need 2 more people to answer. One more person to answer. Who is it? Oh, okay. There it is. There it is. All right. So again, a couple of people got this one wrong, but that's okay. All right. The answer is in fact C. Right. The answer is in fact C. It's definitely not B, because remember the Ka. Right. The Ka equals the product over reactants. Right. So it can't be that. But it does equal, the hydrogen ion concentration does equal the conjugate base concentration. Okay, in this case, the conjugate base was the formate ion, right? So this is the last thing we'll talk about today, because you'll need it for discussion section today. Okay, the method to follow in calculating pH using the Ka, right? The first step you gotta do is write the equation for the ionization equilibrium, which I showed you how to do that a second ago. The second to do is write the equilibrium constant expression, right? Which is the products of the reactants thing. Ka equals the products of the reactants, or you could say Ka equals the conjugate base times the conjugate acid divided by the original acid, right? And then set up your ice table, right? And then do the substitution and solve for x, right? That's how you're going to do this, okay? So here's the example, okay? I have now acetic acid here, right? I want you to calculate the pH from a 0.3 molar solution of acetic acid, right? And it says at 25 degrees. Do you need that number? No, you do not need 25 degrees. So don't freak out when you have a leftover number. So the equation is then this: acetic acid plus water makes the hydronium ion and what? The acetate ion, right? And so the Ka expression will be Ka equals the hydronium times the acetate divided by what? The original concentration, okay, of the acid, which in this case was 0.3 molar, right? So you've got that equation now. You've got to set up this ice table, right? Remember, acetic acid here becomes hydronium ion plus acetate, and our initial concentration of the acetic acid was what? 0.3, and our initial for hydronium and acetate is what? 0, right? Does that make sense so far? Okay. So what is the change in concentration going to be? Well, the change in concentration will be, of course, we're going to be losing X, because we've got to solve for x. We're going to be losing x from the original concentration of acetic acid, but we'll be gaining x, right, plus x and plus x for both the hydronium and the acetate because they're going to be the same concentration, right? Because it's a 1-to-1 molar ratio between the hydronium ions and the acetate ions. And so, in the end, then, we have our equilibrium concentrations being 0.3 minus x for the acetic acid, and then just x and x for both the hydronium ion and the hydroxide ion. Okay, that's helpful because now we can set this up, right? We can set this up where we can plug in our variables. We know that hydronium ion concentration from the table was x. We know that acetate was x from the ice table. And then we know that the acetic acid was zero point 0.3 minus x, right? So this is the part where you say thank you to me because we know for a fact that when it is a weak acid, right, the number is like 5.0 times 10 to the negative 5, right? It's a really small number, right? So if you assume that x is so much smaller than zero point 0.3, right, then all you have to do is just drop the x, right? You can just drop that x because you know that for a weak acid, the number is so small. This association is so small. It's like to the negative 5 or negative 4, negative 6 or whatever it is, right? So it's almost zero anyway. And so if you drop that and just make that zero, all you have left at the bottom then is what? Just 0.3. Why does that make that easier for you to solve this expression? Why are you thanking me for this? Exactly right. Now you don't have to do the quadratic equation anymore, right? Because you no longer have a 2x term, right? Or a bx term for the quadratic. Does that make sense? You look confused. You remember from the last one we did, I made you do the quadratic equation to figure it out? Because you had like ax squared plus bx plus c, right? When you figured out what the expression is, right? The reason why that was is because you had to figure out what this x was right here after you FOILed it, right? But now I'm telling you, for weak acids, just for weak acids, right? You can assume that that x is 0. So that just drops one of those terms, right? And so now the equation you get then is just going to be the Ka, right, equals the Ka equals 1.8 times 10 to the fifth, right? And then all you have now then is this here, x squared from that up there divided by 0.3. Instead of saying x squared divided 0.3 minus x. Does that make sense? Having that minus x there makes you have to do the quadratic equation. Does that make sense? But since you don't have to do it anymore, because I'm telling you it's 0, right? It makes it a lot easier, right? All you have to do is now solve for x squared, right? By the way, this Ka right here is a number that everybody knows. It's from that table that I showed you before. Oop, went too far, right? Here's acetic acid, right? Right there. So you can find it on a table, okay? And so you know that the Ka is the acetic acid Ka equals x squared divided by 0.3. So you solve for x and you get 2.3 times 10 to the negative 3, right? Does that make sense? Everybody got that? So if x equals that, right, all you have to do is take the concentration of this, right, by doing the negative log, because this is a concentration, and if you do the negative log of the hydronium ion concentration, what do you get? You get the pH. Does that make sense? I'm seeing lost faces out there. I'm looking at everybody. You just happen to be looking at me when I was looking at you, but I'm looking at everybody. Does that make sense? Okay. Does everybody know how to solve for x here? You have 1.8 times 10 to the negative 5 equals x squared over 30. You just get the numbers on one side, and then you'll have left over just x squared, and then you take the square root of both. Right? And that's how you get the 2.3 times 10 to the negative 3, right? And the thing about it, though, is that that just gives you the hydronium ion concentration. The problem asks you for the pH. How do you get the pH from the hydronium ion concentration? You take the negative log of the pH. Negative log of the hydronium ion concentration, and you get the pH. Make sense? I could just make it hard on you and say, no, that's not zero. Actually put in there, you know, leave that there. But then you have to use the quadratic equation. But I'm a nice guy. Well, you didn't seem very happy about it a second ago. No one even said thank you.
Well, because we're I'll say thank you after I watch the
I'm just saying, like, no one even would realize that I helped you out there, except for one person that said you don't have to use the quadratic equation anymore. Like, come on, guys. If you're not excited about it, I won't make it easy for you. All right, so when evaluating a Ka expression of a weak acid, which term is so small that we can assume that it's zero? Which term is so small that we can assume that it is zero? Yes, that is correct. This is the last thing we're doing. You just really needed to go through that to be able to work the problems in discussion. I was really hoping that I get a, more of gratitude from that. But
I promise you, when work starts and we have to start doing stuff, I'll be like, okay, well, thank you for that. Whenever I'm watching this video on later, I'll be like, oh, wow, that's why he did it. It's gonna click eventually.
Okay. Okay, I'll give you that. I'll let you. Okay.
You know it's gonna click eventually.
It will.
But until then,
All right. So the vast majority of you got that one correct. Again, I'll have to see who that was there that got. Two people got this one wrong. Oh my God. Holy crap. Okay. For those two who got this one wrong, make sure you remember, okay, that it's x minus right here that you can assume is zero. Because right here, right, this x minus right here is the one that's so small, we can assume it's zero because it's what? A weak acid, right? So it's going to have a number that's going to be times 10 to the negative 5 or times 10 to the negative 4. So that's why you can assume that's zero. Don't assume anything else is zero. Just assume that that is zero, okay? On a weak acid. I'm going to go look in here and see who answered this incorrectly. Give him a good talking to about that. That being said, before you go to the discussion, though, this only works in a weak acid, okay? If you're doing a regular, just a run-of-the-mill chemical equilibrium problem like we did last time, you have to use the quadratic equation, okay? But if it's a weak acid, you can assume that the minus x is zero. And that ends today's lecture.